Welcome, my friends. In this video, we will continue to use trigonometric identities to prove further identities. Specifically, in this video, each identity that we prove will involve either an even or odd identity. Let's look at our first problem. We are asked to prove the identity cosine of negative x divided by 1 minus sine of negative x is equal to secant of x minus tangent of x. Recall that the process of proving a trigonometric identity involves choosing one side of the equation to work on and then manipulating that side with algebra or trigonometric identities until we reach the other side. We complete our proofs in two columns. In the first column, titled Statement, we will show our work. In the second column, titled Rule, we will justify the work in the statement column using either a trigonometric identity or some form of algebra. Let's work with the left-hand side of this equation. We have trigonometric functions that involve negative arguments. If that's ever the case, you can get rid of the negative arguments by using either the even or odd identities. Cosine is an even trigonometric function. That means cosine of a negative angle is the same thing as cosine of a positive angle. So we can simply drop the negative sign, and that won't change the problem. As for sine is an odd trigonometric function, which means that a negative argument will result in a negative function. So that means if we want to get rid of the negative argument, we can simply change the sign of the function. So instead of having 1 minus sine of negative x, we will have 1 minus negative sine of x. We justify these steps by the even and odd identities. Cosine of negative x is the same thing as cosine of x, and sine of negative x is equal to negative sine of x. Let's simplify this a little bit. We have cosine of x divided by 1 plus sine of x, because 1 minus negative sine of x is equal to 1 plus sine of x. At this stage, it might be unclear what you should do next. There's no trigonometric identity that's popping out at me looking at this expression. Generally, when you have terms that are added in your denominator, there are two things that might work. One thing is to get a common denominator between the terms in your denominator. Sometimes that can help simplify the problem, and we'll try that approach on a separate problem. Another approach is to multiply the entire expression by the conjugate of the denominator divided by itself. The conjugate of two terms is the same two terms, but with the sign in the middle changed. So the conjugate of 1 plus sine of x is 1 minus sine of x. When you multiply by the conjugate, the two middle terms in FOIL will cancel each other out. Multiplying by the conjugate is a good idea when the result will be a trigonometric identity, so sometimes you might have to think ahead a few steps. Let's see what we get when we simplify this. On the numerator, we will just have cosine of x times 1 minus sine of x. I could distribute this out, but I'm going to leave this as is for now. On the denominator, we are multiplying conjugates, 1 plus sine x times 1 minus sine x. We have the exact same expression, with the only difference being the sign in the middle as plus or minus. If that's the case, the middle two terms in FOIL will cancel. We will simply have 1 times 1 for the first terms, which is 1, and then sine of x times negative sine of x, which is negative sine squared of x. The middle two terms would be 1 times negative sine of x, and sine of x times 1, which would cancel each other out. We justify this step by simplification. First we multiplied by the conjugate, and then we FOILed out the denominator. We use the special rule for conjugates, that when you multiply conjugates, you just have to multiply the first and last terms of FOIL, so we get a squared minus b squared, which in our case was 1 minus sine squared. At this stage, it should be clear that we made the correct decision, because 1 minus sine squared is a Pythagorean identity. 1 minus sine squared is the same thing as cosine squared. This is an algebraic manipulation of the identity sine squared plus cosine squared is equal to 1. Therefore, we can replace 1 minus sine squared with cosine squared in our expression. At this stage, we have cosine to the first power divided by cosine to the second power. One of the cosines will cancel. We will be left with 1 minus sine of x divided by cosine of x. We can split this into two fractions, 1 over cosine of x minus sine of x divided by cosine of x. We justify this by algebra, simplification, and then splitting the fraction. Be very careful with splitting fractions. Splitting fractions typically only works when you have a single term in the denominator and multiple terms added or subtracted in the numerator, and not the other way around. So in this case, we had multiple terms in the numerator over a single denominator, so we could split that into 1 over cosine x minus sine x over cosine x. At this stage, we recognize that 1 over cosine of x is the same thing as secant of x, so we can rewrite that as secant of x. Also, sine of x over cosine of x is just tangent of x, so we can rewrite that as tangent of x. We justify this by the reciprocal identity for secant and the quotient identity for tangent. At this stage, we are finished with the proof. We have manipulated the left-hand side of the equation so that it matches the right-hand side. Let's try another problem. We are asked to prove the identity cosecant of negative x minus sine of negative x is equal to negative cosine of x times cotangent of x. Let's start with the left-hand side. Again, we have trig functions with negative arguments, which means we should use either the even or odd identities. Recall that cosine and secant are the only two even identities. That's the case where you can simply drop the negative sign. All the other trig identities are odd, meaning that if you want to get rid of the negative sign on an argument, you have to change the sign of the function. So changing the sign of each of our trig functions, we will have instead of positive cosecant, we will have negative cosecant of positive x, and then instead of minus sine of negative x, we will have plus sine of positive x. All we've done is change the argument from negative to positive and change the sign of each function, from positive cosecant to negative cosecant, and from negative sine to positive sine. We justify this with the odd identities for cosecant and sine. Cosecant of negative x is equal to negative cosecant of x, and sine of negative x is equal to negative sine of x. At this stage, it might be unclear what you should do next. Our goal is to get negative cosine of x times cotangent of x. So eventually we're going to have two terms that are multiplied together, but here we have two terms that are added. If that's the case, you probably want to combine your terms in some way, and the way to do that would be to get a common denominator. Let's first change cosecant to 1 over sine, using the reciprocal identity. So we will have negative 1 over sine plus sine. Then if we want to get a common denominator, we need a denominator in the first place on our second function. We have a denominator of sine on the first term, and we have no denominator, or I guess you could think of a denominator of 1 on our second term. To get a common denominator of sine on both terms, we can multiply the second term by sine over sine. This won't change the problem at all because we are just multiplying by 1. Sine over sine is just equal to 1. Simplifying, we will get negative 1 over sine x plus sine squared x, since we have sine of x times sine of x, divided by sine x. Now we can combine our two fractions, which both have the same denominator of sine of x. We will have negative 1 plus sine squared of x divided by sine of x. This is very close to the trigonometric identity 1 minus sine squared, which is equal to cosine squared. If we factor out a negative 1, we will match the identity. We have negative 1 minus sine squared of x. We justify all of these steps by algebra, first getting a common denominator and then factoring out the negative sign. At this phase, the inside of our parentheses matches the Pythagorean identity of 1 minus sine squared is equal to cosine squared. This is an algebraic manipulation of the identity sine squared plus cosine squared is equal to 1. I always remember to myself that 1 minus either sine squared or cosine squared gives you the other one. So in this case, 1 minus sine squared gives me cosine squared. Therefore, I can replace 1 minus sine squared with cosine squared in my function. And of course, I still have the negative sign out front. Now I'm getting a little bit closer to my goal. I'd like to have negative cosine times cotangent. Now I remember by the quotient identity that cotangent is the same thing as cosine over sine. I have negative cosine squared. Cosine squared is the same thing as cosine times cosine, so maybe I'll rewrite this as negative cosine times cosine. At this stage, you can see the cotangent. Cotangent is cosine over sine, so I can replace that with cotangent in my problem. At this stage, we have finished our proof. We have shown that the left-hand side is equal to the right-hand side by using trigonometric identities and algebra. We are finished with our problem. Let's try this problem. We are asked to prove the identity 1 minus cosine of negative x divided by secant of negative x minus 1 is equal to cosine of x. Let's start with the left-hand side. Once again, we have negative arguments, which means we should use either an even or an odd trigonometric identity to simplify our problem. Specifically, cosine and secant are the only two even trig functions, which means you can simply drop the negative sign on an argument. So simplifying, we will have 1 minus cosine of positive x divided by secant of positive x minus 1. This is due to the even identities. Cosine of negative x is the same thing as cosine of positive x, and secant of negative x is the same thing as secant of positive x. At this stage, it might be unclear what to do next. We're at a similar point to where we were a few problems ago, where we have two terms that are added or subtracted in the denominator. Last time when we were at this stage, we multiplied the entire problem by the conjugate of the denominator over itself, which in this case would be secant of x plus 1 over itself. That might not be a very good idea in this problem because the numerator is two terms rather than one term, and we would have to FOIL everything out with the numerator, most likely complicating things. So typically, multiplying by the conjugate over itself is not a very good idea if you have multiple terms in your numerator. It might still work, and maybe you should use that as a last resort, but there might be a better option. Another option is to try to get a common denominator between your two terms in the denominator. That's what we'll try to do here. Let's first change secant to 1 over cosine using the reciprocal identity. Then we want to get a common denominator between the terms in the denominator, so we want to have a cosine in the denominator of our second term. Let's multiply by cosine over cosine. We will get 1 minus cosine over 1 over cosine minus cosine over cosine. Now our two terms in the denominator have a common denominator, and we can combine them. We will get 1 minus cosine divided by 1 minus cosine over cosine. Since these two terms had a common denominator, we could combine them on one fraction, which is 1 minus cosine over cosine. At this stage, you can reciprocate the denominator and multiply. We will have the numerator of 1 minus cosine multiplied by the reciprocal of the denominator, which is cosine over 1 minus cosine. At this stage, something very nice happens. We notice we have 1 minus cosine divided by 1 minus cosine, so those expressions will cancel. We will be left with just cosine, which is exactly what we wanted. We justify these last few steps by algebra, first getting a common denominator, then reciprocating, multiplying, and canceling. We are finished with our proof. Alright my friends, that finishes all the proofs I wanted to do in this video. I know some of these proofs can be very difficult, and sometimes it's not clear what your next step should be. I encourage you to re-watch this video and take very careful notes about the steps that I took and why I took them. Sometimes you will try one approach in one of these problems and work on it for a while and realize that that approach is not working. It can be very frustrating sometimes, so if you are working on a problem for more than 10 or 15 minutes, maybe take a break and try to come back to it later. Alright my friends, that finishes this video covering some more advanced proofs related to trigonometric identities.